This is Dr. Masood Yusuf from the Division of Science and Technology, University of Education, Lahore. I am going to be your instructor for the course Introduction to Material Sciences. This video lecture will summarize types of defects in a quick way. First of all, types of defects based on stoichiometry will be discussed. Among stoichiometric defects, Schottky, Interstitial, and Frenkel defects will be discussed. Another type of defects based on stoichiometry are non-stoichiometric defects. They are mainly anion vacancies, defect due to presence of extra cations at interstitial sites, defect due to the deficiency of cations. The second type of classification of defects is based on dimension. Under this classification, we will discuss point defects, which are zero-dimensional defects, and then there are extended defects which consist of one-dimensional, two-dimensional, and three-dimensional defects, also called dislocations, grain boundaries, and bulk defects respectively. Lastly, study material will be furnished that will help students in order to gain further understanding over aforementioned topics. Let us study defects. First of all, we would like to discuss types of defects based on stoichiometry. As you know, stoichiometry is the relationship between the relative quantities of substances taking part in forming a compound, typically a ratio of whole integers. Stoichiometric defects can be categorized into stoichiometric defects and non-stoichiometric defects. Stoichiometric defects are those that do not disturb the stoichiometry of the compound, whereas in non-stoichiometric defects are defects in crystal structures that disturb the stoichiometry of the crystal. For example, the stoichiometry of hydrogen and oxygen in water H2O is 2:1. Similarly, for iron oxide, also known as ferrous oxide, has the formula FeO, having stoichiometry of the iron and oxygen as 1:1. Whereas if we have Fe 0.96 O, it means it is also a compound resulting from the defects in the compound FeO and is an example of non-stoichiometry. Stoichiometric defects can further be classified into Schottky, interstitial, and Frenkel defects. Schottky defects: in these defects, equal number of anions and cations are missing from the latest sites so that electrical neutrality is maintained. For example, in this left hand side panel figure, you can see a compound NaCl, and you can see that equal number of Na and equal number of Cl ions are missing from this structure. So stoichiometry is not disturbed. That's why this Schottky defect is a stoichiometric defect. And as equal number of sodium and chlorine ions are missing, so the whole crystal structure is neutral. Interstitial structures. Interstitial defects are variety of crystallographic defects where atoms assume a normally unoccupied site. For example, in this above figure showing atoms represented by blue spheres, you can see there is one atom missing from this site, and it is occupying a site which is usually not occupied. So this type of defect in which atom is missing from a normal side and is occupied at a unusual site is called interstitial defects. And this is also a stoichiometric defect because the total number of atoms, the stoichiometry is not disturbed. Frenkel defects. If an ion is missing from its latest site, causing a vacancy or a hole there, for example, in this diagram on the right hand side, you can see it is silver chloride and silver Ag is missing from one of the latest site, causing a vacancy or hole, and it is occupied the interstitial site so that electrical neutrality is maintained, and it is this missing silver is occupied at another interstitial site. So one question arises: what is the difference between interstitial and Frenkel defects? In both interstitial and Frenkel defects, in interstitial defect take place in an ionic solid, in non-ionic solid. So this is a non-ionic solid, and whereas Frenkel defects takes place in ionic solid where we have cations and anions. So this is the main difference between Frenkel and interstitial defects. Let us study now non-stoichiometric defects. They can be mainly classified into anion vacancies, defects due to the presence of extra cations at interstitial sites, defects due to the deficiency of cations. Let us discuss these non-stoichiometric defects one by one. One thing we should keep in our mind that in non-stoichiometric defects, the stoichiometric, the ratio between elements will be changed. anion vacancies. In this non-stoichiometric defect, a negative ion may be missing from its lattice site, leaving a hole which is occupied by an electron, thereby maintaining a electrical balance. So, for example, in this figure below, you can see positive and negative anions, and one of the negative ion B is missing from its site, leaving a hole which is occupied by an electron in order to maintain the electrical neutrality of the crystal. So this type of defect is called anion vacancy, as the number of negative B ions is less than of the pure sample, so stoichiometry is changed now. So that's why it's called non-stoichiometric defect. And this trapped electron, they are called F centers or color centers because they are responsible for imparting color to the crystal. Another non-stoichiometric defect is defect due to the presence of extra cations at interstitial site. So this defect is caused by an extra cation occupying the interstitial site. To maintain electrical neutrality, an extra electron is also present in some other interstitial site. This defect is similar to Frenkel defect and is formed in crystals having Frenkel defects. So for example, this left hand side panel figure, you can see that there is an extra cation present at interstitial site, and to maintain electrical neutrality an extra electron is also present. So due to the presence of extra cation, stoichiometry is changed, and that's why this is a non-stoichiometric defect. One of the example relating to this defect is that when we zinc oxide is a white or colorless solid at room temperature, but when zinc oxide is heated, it loses oxygen and turns yellow. So when we heat zinc oxide, it loses oxygen and it produces zinc plus 2 cations and extra electrons. On heating, the extra zinc plus 2 ions get trapped into the interstitial sites. So these are shown in the figure, and the released electrons get trapped in its neighboring interstitial sites, and thus they maintain the electrical neutrality. So when the zinc oxide is heated, it gives zinc plus 2 cations and oxygen. Oxygen is released, so and zinc is still present. The stoichiometry is changed due to the release of the oxygen. Crystals with either of these metal excess defects contain some free electrons as shown in this figure. Hence, such materials are N-type semiconductors. Another non-stoichiometric defect is defect due to the deficiency of cations. This kind of metal deficiency defect is created when a metal ion goes missing from its original site. So, for example, this right hand side figure, you can see that we have cations and anions, and cation is missing from these two positions. To maintain the charge neutrality, say metal ion having higher positive charge is added to occupy vacancies created in the crystal. So to maintain the electrical neutrality, these two vacancies, they can be replaced by only one cation having charge m plus 2. The original sample has cations with charge m plus 1. So 1 m plus 2 cation is replacing 2 m plus 1 cations. As this metal ion has higher positive charge, it will occupy only some of the sites. So it is occupying only one site to balance the overall charge, and other site will be left vacant. So this type of defect is called defect due to the deficiency of cations, as one site is occupied with cation but the other site is missing. Stoichiometry is changed, so this is a non-stoichiometric defect. Metal deficient materials conduct through positive holes as shown in this right hand side panel. So we have deficiency and thus behave as p-type semiconductor. Please remember that the 2 m plus 1 charges are cations are replaced by only one m plus 2 cation, so the charge neutrality is maintained. Example of this type of defect: if molten NaCl containing a little strontium dichloride as impurity is allowed to cool, so we have this NaCl, and if it is molten form, in molten form, and some little containing a little impurity such as strontium dichloride, so at some later sites Na plus ions are substituted by strontium plus 2 ions. So you can see two, for example, two Na cations are missing and only one strontium ion is enough to replace two Na ions. So this is a defect. So metal having cation deficiency, as only one cation is replacing two cations and stoichiometry is changed, therefore it is a non-stoichiometric defect. Let us classify the defects in another way. So we can also classify defects on the basis of stoichiometry as we have defined earlier, but we can also classify defects based on dimension. Classification of defects based on dimension is very easy. For example, we can classify them into point defects and extended defects. And point defects can further be classified into stoichiometric and non-stoichiometric defects that we have already studied. Point defects are zero-dimensional defects. It means these are such defects that happen only on a one site. Zero dimension means that a dimension which is not extended in which is constrained like a point. So that's why it's called point defect. Whereas extended defects can be further classified into dislocations, which are 1D or linear defects happens along a line, grain boundaries, which are 2D or planar defects happens along a XY plane. Lastly, bulk defects, which are 3D or volume defects. So as we have already covered point defects, which are stoichiometric and non-stoichiometric defects, let us focus on extended defects. Extended defects can be classified into three types, and let us study them one by one. Dislocation 1D or linear defects. Dislocations can be visualized as being caused by the termination of plane of atoms in the middle of crystal. So a line or 1D arrangement of atom is missing in a crystal and is not extended throughout the crystal. Such a defect is called 1D or linear defect. In such a case, the surrounding planes are not straight, but instead they bend around the edge of the terminating plane so that the crystal structure is perfectly ordered on either side. Let us visualize this, but before this, dislocations can be classified into edge dislocations and screw dislocations. And please remember, mixed dislocations having intermediate between edge and screw dislocations can also happen. Edge dislocation. An edge dislocation is a defect where an extra half plane of atoms is introduced midway through the crystal, distorting nearby planes of the atoms. So you can see this is the extra half plane of the atoms and it is not extended throughout. So it distorts the nearby plane of atoms because it needs some space to be inserted. When enough force is applied from one side of the crystal structure, this extra plane passes through the plane atoms, breaking and joining bonds with them until it reaches grain boundary. So this extra half plane can move throughout this crystal structure until it reaches another crystal with different orientation, which is also called grain boundary. Key terms. The dislocation has two properties. Line direction, which is the direction running along the bottom of the extra half plane. So this extra half plane, it moves in a certain direction, that is called line direction. Burger vectors, which describe the magnitude and direction of distortion of the lattice. So when this extra half plane move along the line direction, so there is a perpendicular direction of distortion which is called Burger vector. In an edge dislocation, the Burger vector is perpendicular to the line direction. Screw dislocations. In comparison, a structure in which the helical path is traced between the linear defect by the atomic planes in the crystal lattice. So screw dislocation, as you can see that the name suggests that this kind of dislocations is similar to a screw. So in screw you can see a helical path. So you can see this type of defect or dislocation happens when we move from one plane, and when we cover the 360 we happen to be below that point. Its name screw dislocations because if we start at one point on the crystal lattice and walk a path around that point, which can be it can be seen with the green color, and walk a path around that point, we end up immediately below that point. And if we continue to do that, we would end up below that point again, and so on. So if we start from this, we will not, after covering 360, we will not reach the same point, but we will reach directly below that point. Such a dislocation is called screw dislocation. Grain boundaries, 2D or planar defects. A grain boundary is the interface between two grains, which are also known as crystallites, in a polycrystalline material. So this is a polycrystalline materials having grain 1 and grain 2. Polycrystalline material means it is the same crystal but having some patches of crystals or grains of crystal with different orientation. The particles are small single crystals of dimensions generally between 5 and 100 micrometer, randomly oriented in the solid. These particles are called grains. So the size of this grains shown in the figure may be between 5 to 100 micrometer. As you can see from the right hand panel figure, so we have silicon carbide, and you can see that they are misoriented, and the where they meet two crystals, this is called grain boundary. Grain boundaries can be low angle grain boundaries or high angle grain boundaries. In low angle grain boundaries are those with the misorientation less than about 11 degrees, whereas in high angle grain boundaries whose misorientation is greater than about 11 degrees. The last type of extended defect is bulk defect, 3D or volume defect. As the name suggests, this type of defect is along all three axes, x, y and z axis. The defect in 3 dimension that change the crystal pattern over a finite volume is called bulk defect. They can be pores or cracks. These defects are introduced usually during processing and fabrication operations like casting, forming. The image on the right hand side is a void. You can see this is a kind of void in a piece of metal. The image was acquired using a scanning electron microscope. This is a 3D defect. Here is the list of study material that consists of some important books on material science, and one of the educational link from UK, which is also helpful in order to study different articles on the aforementioned topics that we have covered in this video lecture. Thank you for having me. That's all.